I'm Andreas Hamberger, and this is the Hamberger Report, where I cover AI governance, enterprise architecture, and the technology decisions that actually matter to the people who have to make them. If you find this useful, subscribe and hit the like button. It helps more professionals find the channel. Now let's get into it. Shadow AI adds $670,000 to the average data breach. Not because of sophisticated zero-day exploits, not because of nation-state attackers, because AI tools were deployed without security oversight, because it works on my laptop, became the implicit production standard for systems touching sensitive data. I'm Andreas Hamberger. This is the Hamberger Report, where I cover enterprise architecture in the age of AI agents. If you deploy machine learning models, that $670,000 figure is the price tag for the gap between what you know about machine learning and what you probably do not know about network security. This episode exists to close that gap. IBM's 2025 Cost of a Data Breach report found that 13% of organizations experienced breaches involving AI models or applications. Of those, 97% lacked proper AI access controls. The pattern is consistent. AI systems are being deployed faster than the security architecture can govern them. That brings us to the concept at the center of this episode: zero trust. The traditional security model operated on a simple premise: build a wall around your network, verify identity at the gate, and trust everything inside. That is the castle and moat approach. It worked adequately when users sat at desks inside corporate buildings and applications ran on servers you could physically point to. Long model is now obsolete. Your ML training pipeline pulls data from a cloud data lake in Sydney. Your model is served from a container in Azure. Your API consumers span mobile applications, web services, and 3 internal systems running in different network segments. The concept of inside the network has no meaning in that environment. Zero trust replaces the perimeter model with a single principle: never trust, always verify. Every access request, whether it comes from a human user, an API call, or an automated ML pipeline, is treated as potentially hostile until verified. Trust is not granted by network location. It is earned through continuous verification of identity, device health, and behavioral context. The market reflects the urgency. Zero trust architecture is estimated at $38 billion in 2025, projected to reach $87 billion by 2030. Yet Gartner projects that by 2026, only around 10% of large enterprises will have a fully mature program, up from less than 1% in 2023. The gap between recognition and implementation is exactly where AI practitioners can make the most difference. Three terms that security professionals use interchangeably in casual conversation have precise, distinct meanings. Getting them wrong creates vulnerabilities that no amount of model accuracy can compensate for. First, identity. Identity answers the question, who or what is making this request? For human users, identity is established through accounts and credentials. For AI systems, it is more complex. Your ML pipeline is not a person. It is a workload, a service, a process. It still needs an identity, one that is unique, auditable, and revocable. Every component of your AI system needs an identity that can be independently verified. Second, authentication. Authentication answers, can you prove you are who you claim to be? This is the verification step. For humans, it means passwords or security keys. For your ML model serving endpoint, it means cryptographic certificates, signed tokens, or workload identity attestation. A static API key embedded in your deployment configuration is technically authentication, but it is the weakest form available, equivalent to taping your house key to the front door. Modern authentication for AI workloads uses short-lived, automatically rotated credentials that expire in minutes, not months. Third, authorization. Authorization answers, now that I know who you are, what are you allowed to do? This is where most AI deployments fail. Authentication without proper authorization means your verified ML pipeline can access every data source, call every API, and write to every storage location it can reach. One concrete example. Your sentiment analysis model needs read access to customer feedback records. It does not need write access to the customer database. It does not need access to financial records. It does not need the ability to call external APIs. Each of those unnecessary permissions is an attack surface. If that model is compromised through prompt injection, data poisoning, or a supply chain attack, the blast radius is determined entirely by what the model was authorized to do, not by what it was designed to do. That is why authorization is not a configuration detail. It is an architecture decision, and it needs to be made before your model goes anywhere near production data. Network segmentation divides your infrastructure into isolated zones, each with its own access controls. For AI practitioners, this is where principle meets deployment architecture. In an unsegmented network, a compromised component can communicate with every other component. If an attacker gains control of your model inference endpoint, they can reach the training data store, the logging system, the authentication service, and potentially the wider corporate network. The blast radius is unlimited. Segmentation limits that blast radius. Your model inference endpoint sits in one zone. The training data sits in another. The logging system sits in a third. Communication between zones is explicitly permitted, monitored, and constrained. A compromised endpoint can only reach the specific resources it has been granted access to, mediated by policy enforcement points that inspect every request. The practical takeaway: if your deployment configuration does not explicitly define which network endpoints your model can communicate with, it can probably communicate with all of them. That is not a feature, it is a vulnerability. Which brings us to the single most important security concept for AI practitioners: least privilege. Every component should have exactly the permissions it needs to perform its function, and no more. For AI workloads, that means constraining 5 dimensions of access. Data access. Your model reads only what it needs for its specific task. Training pipelines need access to training data during training, not during inference. Compute resources. Your training job needs GPU access during training, not when it is idle. Permissions are provisioned on demand and revoked when the job completes. Network connectivity. Egress controls govern what your model can send outbound. An AI system that can make arbitrary outbound connections is an exfiltration vector. Temporal access. Permissions are time-bounded. Just-in-time provisioning grants access when needed and revokes it automatically when the task completes. Operational scope. Your model endpoint might need read access to a database. It does not need to delete tables, modify schemas, or create new users. Scope permissions to the specific operations required, and nothing more. The deployment anti-patterns follow directly from these principles. Shared service accounts across ML pipelines mean a single credential compromise exposes every workload. API keys stored in environment variables are equivalent to writing your password on a sticky note. Training pipelines with persistent access to production data are lateral movement opportunities waiting to be exploited. Model endpoints with unrestricted egress are exfiltration vectors by design. The correction in each case is the same: unique identities per workload, scoped credentials, just-in-time access provisioning, explicit egress allow lists, and strict separation between development and production environments. These are not advanced security concepts. They are the operational floor for any AI system that touches sensitive data. For practitioners in Aotearoa, New Zealand, these fundamentals are becoming compliance requirements. The NZ regulatory framework is increasingly aligning with Zero Trust principles, Information Privacy Principle 3A. Taking effect in May 2026, creates new obligations around data provenance that require exactly the kind of granular access controls covered in this episode. Understanding Zero Trust is not optional for anyone deploying AI in New Zealand's regulated environments. It is rapidly becoming the baseline. The wider picture matters here. Chapter 1 of this series established that the median time to compromise an AI system is 16 minutes, from initial access to full system control. The only architecture that can respond at that speed is one where access controls are granular, automated, and enforced at every transaction. That is not an aspirational standard. That is the floor. Next week, we move to the distinction between AI agents and agentic AI. That distinction determines whether the security model you have just learned scales to autonomous systems. It is a distinction most organizations are getting wrong, and the consequences are already visible in incident logs. If you are an architect or CIO figuring out what agentic AI means for your practice, subscribe. And if you want structured talk of training adapted for the agentic age, the link to my practitioner course is in the description. Subscribe to the Hamberger Report, new videos every day. That is the Hamberger Report for today. If this was useful, subscribe and hit the like button. It helps more professionals find the channel. You will find links to everything we covered in the description below. I am Andreas Hamberger, and I will see you tomorrow.